It's time again for Astronomy Daily Live. Hey, everybody. Hope everybody's doing well out there. You can call me Cosmic, and howdy, howdy. I just erased my tweet. Let me try to tweet this. Hold on one second. I'm gonna put you down. All right, there it goes. I think it's going. Is it going? Is it going? Yes, it's going. Yay. So, hey, everybody, welcome, welcome, welcome. Come on in. Come on into the circle of friends sharing a common passion for the science of astronomy. So, hope everybody's doing well out there in the universe and the world. Was having some fun this morning, doing some artsy work. I don't know if you saw the posts that I made over on my Discord server. What I've been doing for a while is taking um, is going over to the Gaia data set. I don't know what that is. Wait for it to just wait. Um, I've been going over to the Gaia data set and sort of moderately randomly um, uh, picking a field of stars. You can make a query such that you say, okay, I want to look at a 10 arc minute radius centered um, centered on a certain right ascension and declination, right? And what it will spit back is all the stars, and various useful pieces of information about those stars in that field, right? And uh, the the ones that I'm kind of interested in at this point is the position and the magnitude, the brightness, right, of these individual stars. So what I've been doing is I've been um, grabbing that list and then using a plotting program called GNU plot, which in my opinion is one is got to be, well, definitely in the top three of plotting programs that I've ever used. And honestly, I haven't used a lot of those. Oh, I need to, oh, too late. Oh, it's not too late. It's not too late. I can do it. Come on. These live streams freeze my Linux machine, and I always forget to stop it. Before I do that, Bobby is in the house. Gilles is in the house. Hey, everybody. Nice to see you in the chat. I'm attempting to pop the chat out, but my poor Linux machine is on its knees. It's still functioning. It's still functioning. It's going to slowly recover now, slowly recover. I'm popping the chat out so I can just get rid of this window completely. So while that's going, I'm going to sort of be distracted over here. But what so what I've been doing with that list of stars is using a plotting program called GNU plot, which is incredibly powerful. I'm just scratching the surface in terms of its capabilities. Oh, this poor Linux machine. But what I've been doing is I've been so plotting the positions of the stars, right? And then just drawing lines between each of the stars. And there's nothing really interesting there. I mean, it makes kind of a cool pattern. And, so I've been trying various things to maybe make it a little bit more interesting. Because it's an SQL query, I can actually tell it to tell Gaia to order the output of these list of stars by like right ascension or declination or magnitude or actually any of the data points that it has access to. So I did that, and it's like, yeah, it's not very interesting either. So this morning, I'm like, okay, I'm gonna try. Um, uh, I can't easily instruct Gaia to um, send me a list of these stars ordered by how far away they are from the center, right? So what I did is I actually chose the star field that includes Gamma Velorum, which is the star slash cluster that we looked at yesterday. And, that was just they're on the top of my mind. So it's like, okay, just go with that. It doesn't really matter, right? It doesn't matter what part of the sky, right? And so yeah, I chose a 10 arc minute radius around the star Gamma Velorum, and it came back with I've probably still got the query here. Yeah, it came back with 7,254 stars, right? So the positions and magnitudes, brightnesses of 7,254 stars are within a circle smaller than the size of the full moon, right? So just a very, very, very small piece of the sky. And I sort of did exactly the same thing. The only thing that I changed, I think, no, I've done this before too, is that I made the lines like really, really thick, and I colored the lines by looking at the brightness of the star and just doing a very, very, very simple transformation uh, to make each line uh, um, change color, right? Change color. So yeah, I have done that before, and it's like, that's not very interesting either, right? So it's like, just plotting the stars and connecting them all with lines of various thicknesses and colors and all that. It's like, um, trying to see if connecting them all by right ascension or declination. It's like, yeah. Well, the thing is, right, is that a couple of days ago, I figured out how in GIMP to actually combine images in these layers, right? So instead of just um, stacking the layer, I can combine them in various ways, right? And in order to uh, uh, um, and then I proceeded to go to Mars and go to the Hubble Space Telescope and try to grab some images and play with the colors and um, see what can happen, right? But then it's like, well, I can do the same thing for these plots I'm making with the Gaia data, right? I can now combine. I can add them. I can subtract them. I can divide. I can multiply them. I can have combinations. So say that I have four raw um, um, images, right? These plots, right? I can output these plots as PNG files or JPEGs, whatever I want, right? Um, I think I'm outputting them in PNG in this case. Arbitrary choice. And I don't have an example of that to show you, but that doesn't really matter. So say that I have like four of these in four different layers inside of GIMP. So now GIMP is the GNU image manipulation program, and there's only one other um, image display program that I've ever used that is better than GIMP. Um, and yeah, and that's a program that's called XV, and I don't even know if XV exists anymore. It's a Unix thing. Um, so I don't know if XV exists anymore. I should probably try to find out and see if I can get it installed on at least one of my Linux machines here, because XV by far is fantastic. Now, for image editing, if you want to be able to do sort of this image math and stuff, XV is not the thing. What you want to use is GIMP or its um, ugly cousin, Photoshop. um, it's uh, it's hydrogen hydroxide tonight, HOH, which like its twin, dihydrogen monoxide, is the most amazing molecule in the universe, right? Absolutely mind-blowingly amazing, and pretty tasty. I've got about 10 to the 23rd of those molecules in this mug, and yeah, I'm aiming to sort of absorb all of those in the next hour or so. Cheers. Ah, freshly brewed too, right out of the tap. Ah, awesome. So yeah, I can take these sort of raw images, GNU plot, which look like garbage, right? I mean, they're really garbagey, but I can combine them, right? I can um, mostly what I was doing was, and I'm not quite sure um, what the difference is between these two terms, but GIMP has a difference function and it has a subtraction function, and I'm not quite sure what the difference is. This is all um, doing or performing mathematical functions on the colors. Yeah. So yeah, I don't know what the difference between doing a difference and doing a subtraction is yet, but regardless, what I was using mainly this morning was the difference function and divide. And when I did that, I came up with some pretty interesting sort of mosaic-y patterns. So it's like, oh, well, finally, I'm seeing something that is sort of, tickling my um, 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 the artistic part of my brain, right? Just sort of going ding, 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 ding. So it's like, oh, okay, well, that's kind of interesting. That's kind of interesting. So I played with that a little bit. I did some edge detection stuff. So I could make it look like odd shaped tiles, and it's like, okay, that's all right. That's all right. And then it's like, okay, well, what else can I do here? What else? And so, yeah, I mean, this has happened all too often, right? I mean, um, I get um, distracted on either a programming project of some sort, trying to solve some kind of a problem, um, or I get into this artistic thing where I'm either, you know, uh, trying to produce, some kind of visual art or some kind of music, and I I could have literally spent all day um, today, but but bills must be paid. Bills must be paid, and work elsewhere must be done. People are counting on me, right? So it's like, okay, look, I have to stop this. I have to stop this. I'll post a few of the interesting ones, and then I'll talk about it, right? So I did that, and I did a few other interesting things, interesting manipulations of the colors and the data and all of that. And um, and I don't know if you saw this or not, but I'm gonna uh, let you see it anyway. I'm gonna pull up my smartphone uh, live stream there, and I'm gonna share the screen. I'm gonna go to infinity, and then let's go. This this will be just a quick tour because I'm yeah, I've barely touched sort of this new uh, means of making some yeah, moderately interesting art. I'm not going to say it's all that great, but it does have its possibilities, right? And this is the first time that I've tried to, or that I've actually seen something that that might come on, that might be interesting, right? Might be a little bit interesting. So here's the first one. So the real interesting thing about this, right, is that this is totally traceable back to the 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 star positions around Gamma Velorum, right? Uh, and it it may not appear that way, and it's not supposed to, right? I'm using that data as sort of as my paint, right? Just as my paint, and maybe you know uh, sort of how I paint, right? But in terms of everything else you're seeing here, that is completely artistic license, right? I mean, I've greatly modified the the um, the inputs to this, But as I said, this is all based on astronomical data, right? It's based on the positions and the brightnesses of these 7,254 stars, right? And yeah, so I just think it's interesting, right? I'm not going to say that this is uh, too incredibly wow. Um, is it something that I would put into a like an art show? Yeah, I probably would. I probably would. So this to me looks like uh, sort of like inverse smoke. And you know what I really should do is just invert this so all the black looks white and the white looks black, and I think it would look a little bit more like swirly smoke. But I've shown this, to people all already, and they see faces and they see, dogs, and I mean, our brains take this and can do lots of things with it. Now this is the same data. This is the same um, star position data and magnitude. I remove the color, and it's like, oh well, that's kind of interesting. So there's that, and then there's this last one, which I posted here, which is this one. And let's see, we can click on that. And this is sort of similar to the first one. It just isn't quite as it isn't quite as dense, and the colors are different, and yeah, and you sort of get like a 3D sense here. It's kind of interesting. Oh yeah, I forgot to zoom in on the other one. You can sort of see these weird contours and things. Now I can hear everybody saying, yeah, that'd be a really cool you know screen background. And in fact, if I add if I um, animated this, it would be a great screensaver. And it's like, oh, I don't want to make screensavers. I want to make visual art. So yeah. But yeah, as I said, that's moderately interesting. What makes it really cool is that it's actually based on real astronomical data, the Gaia um, data release number 2, and this and that's why it's round, right? Because I've taken star positions from a radius out. So one, I mean, in a real incredible stretch of the imagination, you can say that this radius here is about 10 arc minutes or so, and all the stars are inside of that. But I've greatly manipulated uh, um, the original data. But yeah, this is sort of one of probably the first lead that I've had in terms of art in a few months. So I've got a few other ideas that I need to mess around with. I've got a lot more control over the color um, than what I am showing here. So there, yeah, there's just a lot more I can do, and now that I can sort of see this, I can I can I can definitely see some pathways to some interesting things. Don't know where those pathways lead, right? They most of these things, they lead to dead ends where it's just like, oh, that's garbage, right? It's just total crap. But sometimes they don't. Sometimes they open up into these beautiful meadows, and it's like, oh wow, very cool. So cheers. So Tim Robinson has made a few he he made a few comments in yesterday's live stream or the day before, I forget exactly. I think it was the day before, the one where I was showing you how to colorize the Mars images and the HST images, um, so yeah, I forget exactly how it went, but I mentioned FITS, FITS. That stands for Flexible Image Transport System, and it's a scientific, I guess you can call it, data format um, that uh, is pretty standard in terms of astronomical um, data, and that can be all kinds of data, right? It can be an image, it can be a spectrum, it can be, and it doesn't have to be just a single image. It can be what's commonly called like an image cube, right? Lots of images in one file, right? Or lots of spectra. But there are also FITS extensions, and FITS extensions allow you to basically put anything you want, anything. It can be, um, you know, your menu plan for 2019. I mean, it doesn't matter. It can be a JPEG image. It can be, you know, it can be anything at all, right? Um, so I'm not going to get into extensions because that just sort of opens up the entire universe. So Tim had asked, well, what, he he um, um, he did some investigating about fits and sounded a little bit confused about exactly what it is. And so I told him that I would talk about that in this live stream. Um, so I don't know if Tim is still awake. It is. I believe it's like 3:28 a.m. Tim's time. So it's like, really, really, really early in the morning there. So I don't expect him to show up at all. But he will be watching this sometime in the future. So I'm going to do this anyway. And I think I've mentioned FITS files from time to time here um, in the live stream, but I've never actually shown you sort of what they look like. Now, the format of a FITS file is very, very basic, right? Now, as I said, it can get very, very complicated, um, uh, but you know, for like just a single image, right? Like the images I take with this telescope, they're saved in FITS format. And it every FITS file must have at least these two things. It has to have what's called a header, and it has to have data, right? And the header is nothing more than metadata in a specific format, right? Now, there is a FITS standard that was defined, but I don't know the exact details in terms of what's exactly required. We're going to look at a FITS header here soon, um, but these headers are ASCII text. They're so they're basically single byte values, right? That can go from 0 to 255, right? So they're 8-bit values, 1 byte values, which are interpreted as characters. So, and there are, surprisingly enough, 256 characters, right? Including the letters of the alphabet, lowercase, uppercase, all, 0 through 9, um, lots of other characters, right? There's I forget exactly. I mean, the entire keyboard is mapped that way, right? So each key on your keyboard actually corresponds to one of these characters, which is then interpreted and dealt with, right? Uh, so uh, so this header has to be um, uh, ASCII bytes, right? And uh, the header is structured in a way such that you can have that. So there are columns and rows, right? Columns and rows. There are 80 columns, 80 columns, and then there are, oh man, I'm forgetting. I can't believe I'm forgetting that. Oh yeah, okay. So 80 columns and 36 rows makes up a block of data that is 2,880 bytes in size. And um, um, 2880 is one of those magic um, computer numbers that um, pops up from time to time, and I wonder. I'll 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 bet that rings bells in Gilles' head. 2880. Um, so I'm not exactly sure what the exact origin of that is, but it has something to do with fourth, the fourth operating system. I believe had to operate in these maximum size blocks of 2880. Now, you can have as many of these blocks as you want, but the header has to be sized such that it is modulus 2880. Oh, Tim is here. I cannot believe it. Peace, man. you're you're crazy. You're crazy to be up this early or this late. That's just crazy. Um, no, I just started, so no worries at all. So every FITS file needs to have two things. It needs to have a header, and it needs to have data. And I was just talking about um, the format of the header. It needs to be sized such that it's in these blocks of 2,880 bytes, which is 80 columns by 36 rows. Now, those rows are not called rows. Those rows are called cards. They're called header cards. Header cards. And this is where the metadata starts. Each one of these cards is basically uh, comprised of three pieces, right? The first piece is, I guess, what you can call the variable name, right? And I'm going to show you an example here, but um, um, like the number of X pixels in your image. and the number of Y pixels, say, right? Um, so those are the variables, right? The variable names, right? Then the second piece of information in a header card is the actual value itself, the number itself, right? And then the third part, optional, is a comment. So you can make a little comment, which will usually give a little bit of a description of um, what the variable is, right? He's in his chair in front of the PC. Yes, this is FITS, the FITS image file format. It's called um, FITS is an acronym, right, for Flexible Image Transport System. And yeah, I mean, it's extremely flexible, but I'm talking about just sort of the basic uh, required things, right? So each block of data can be 36 of these header cards that can be a maximum of um, 80 columns long. Now, if you're a programmer, okay, the way to deal with FITS header cards is to create what's called a doubly linked list. If you have a doubly linked list, um, then you are gold, right? That is the easiest way to deal with FITS header cards. Yeah, if you ever see anybody struggling, trying to read those things, just whisper in their ear, doubly linked list, doubly linked list will get you there. Yeah, I've written big libraries um, programs to be able to edit these um, um, cards and these FITS headers. So, but as I said, you can have as many of these 2880 blocks as you want, right? And I should have pulled over um, like a FITS image from like a Hubble Space um, telescope um, image, because those headers go on and on and on. There's every kind of data that you can possibly imagine is in there, right? But there sometimes you want to record all kinds of things, um, which sort of gives you a snapshot um, uh, of what the conditions were when you collected your data, right? So um, let's just look at um, let's just look at a header of mine that I will get from one of the FITS images that um, I get from my scope. So I'm going to go over here and we're going to look at this one here, and I'm going to open it with WordPad like that. Okay. So, and I'm going to make this, well, yeah, I don't have to make this any smaller. Okay. So here is sort of a pretty typical FITS header, right? And every FITS header has this first line in it, just like that. Simple equals T, which stands for true. That's a Boolean value. It can either be T or F, true or false, right? So the other useful bits of information, of course, some of this data actually describes the data. Some of this data, metadata, describes sort of the conditions at the time, right? So this bitpix is the number of bits per pixel, right? So in this case, I've got 16-bit data. So if you're a software developer and want to be able to read this data in, that's a very important piece of information, right? N-axis is the number of axes, which in this case is 2, right? And then those 2 are defined. N-axis 1 is usually your x dimension, and N-axis 2 is usually your y dimension. So my images are 765 pixels wide and 510 pixels high. 16-bit data. B scale and B0 have to do with how the data is interpreted, so I'm not going to get into that much. I don't know why they put in this origin thing. Some of this information is just in the software and gets written to the header that I've never changed, right? So I'm not too concerned about recording, the focal length and the aperture size. So that isn't what I'm working with. The two pieces of information here that I do like to have, of course, is the date and the time. And this time is in universal time. So I took this image, and I think the time of the observation is when this when this file is written. So if you have a 2-minute exposure, right? I'm pretty sure that this time of the observation is at the end of that exposure when the file is written, right? So, but in this case, it was written on the 9th of May 2018 at 3:40:36, right? These other things, not quite sure what EXP state is. I'm going to have to look into that a little bit and see what that means. So here's the temperature of the camera at that time. Too many digits here, but it was about 0.19 degrees Celsius or so. Something like that. This filter is marked lunar, but it's actually my clear one. So yeah, I just need to know those kinds of things. Now I could go into the software and actually change that if I want, but I know. The exposure time in this case was 1 second, right? 1 times 10 to the 0 is 1. And then we have this extremely important header card down here that's called end. And end is extremely important, of course, because it tells any software that is written that this is the end of the metadata, right? So if you don't have an end card in your FITS header, the software is going to assume that this whole file is a FITS header, and it's going to try to interpret it, right? So you have to have an end card in there. You have to. Now, as you can see, there's some repeated stuff here for a little while, and then things change, right? Well, what's happened here is that, and I'll show you this in another example, is that, okay, I don't have any more information, right? But as you recall, these headers have to be modulus 2880 bytes. So what all this stuff is here is filler. It's just nulls. It's zeros, right? My program, has tried to interpret those, and um, did as good as it could, but yeah. So all this here is just filler, right? It's just a bunch of zeros, and the information, the actual data, actually starts right there. So the data that's actually stored um, is going to be a list of 16-bit integers. That's all it is, right? There is no color information. There is there's nothing like that at all, right? It's all you get back is this big long list of 16-bit um, integers, right? Well, so now you got to think about what those numbers are representing, right? So what those are showing is the brightness of a particular place on your CCD, right? Now, I can digitize any brightness from 0 to 65,535, right? So if I have, like a really bright star, say, that is so bright that it's actually saturating the CCD, then at those pixel locations, it's all I'm going to get are numbers corresponding to 65535. That's it, right? Because it's just too bright. The intensity is just too bright. It's saturating the CCD, and nothing can be seen, right? But if you don't saturate the CCD, then the little analog to digital converters inside of the CCD can look at the intensity of those things and assign a number to them between 0 and 65535. And that is what that list of numbers is inside of the FITS file, right? So you tell it, right? Look at the header again here. You tell it that this image is 765 by 510, right? Whoop, 765 by 510. So that's 390,150 pixels, right? But each one of these pixels is actually 2 bytes in size, right? 16 bits is 2 bytes. So I can multiply that by 2, and you get a file size that is 780,300 bytes. So hopefully you're following me a little bit there. So yeah, so what you end up with, right, is just this list of numbers, and this is actually the second part of a FITS file, right? You have the header and you have the data, and the data is just this long list, right, of, whoops, 765, can't type, times 510, of 390,150 numbers. It's just a list of numbers. That's all it is. So There's no color information. There's no position information. There's no encoding. There's no compression. There's nothing. There's nothing at all. It's as if you took out a piece of paper and wrote down 390,150 numbers going between 0 and 65535. And that's it. That's all it is. That's all it is. And that's all any kind of information is, right? So now let me show you this next file, which will sort of clarify a little tiny bit more, maybe. So I'm going to make this, I've got to shrink this, I've got to shrink this font down a little bit. So sorry, it's going to get a little bit small, but I have no choice because I got to be able to pack all this information in. These dumb machines. There we go. Go all the way to the top here. So this is just sort of a different way of showing exactly the same thing that I just showed. But now, if you sort of squint your eyes, you can see this column on the left, right? And what that's showing is the byte number of the file itself, right? So each one of these rows is 16 bytes long, right? Because it goes from 0 to 15, and then it starts here with this next row at 16, goes to 31, wraps around, right? Does that make sense? I hope it makes sense, right? So what you can sort of see right away is that, you know, each header card is supposed to be 80 characters long, right? So here's, which is of course 80 bytes long, right? So here's 0, 16, 32, 48, 64. So this blank one is 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76. Oh, here's 80. Yeah. Okay. So the next header card actually starts at byte number 80, right? Makes total sense. The next one starts at 160, 240, 320. So these are all factors of 80, right? Which makes total sense. That's exactly what it's supposed to be. This is a valid FITS header card, or FITS header. So I'm just keeping count of the bytes over here now, right? These little stars, these little asterisks mean that whatever the previous 16 bytes was, it's just repeated until there's a change, right? So that's why we're not seeing 128 and then 144, blah 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 blah, right? It sort of skips those to save space. This is a Unix command. This is actually a command that's called OD. It stands for Octal Dump, but which sounds a little crude, I guess. But it can actually, if you really want to look at the structures of files, be it a FITS file or a GIF, JPEG or anything, you can actually look at the individual bits in your file and see how they change. This is just one of many ways of displaying this kind of data. So here's your header again. Sorry about that. Let's go up. Here's our header, right? And as you can see, it's going along, going along, going along. Okay, here's our end. Here's our end card, right? So byte 200, byte 2480, 81, and 82 spell out END, right? And then there's blanks, which are actually spaces. And then starting at byte number 2560, and I know that this is a little bit hard to see, sorry. Uh, Starting at byte 2560 are these nulls, right? That's what's called a null. That's just, it's sort of like a zero. It's ASCII value 0 as opposed to the ASCII character 0. This is an ASCII value of 0. And look at that. The data actually starts at byte number 2880, just like it's supposed to, right? It's some mod of 2880, right? So the data in this case is 16-bit data. That's 2-byte data. I think these are interpreted actually as what are called unsigned short integers, which means that these actual values can range from negative 32,768 all the way up to 32,767, right? And it's just how these kinds of things are um, um, interpreted by the computer. I can I can change those values inside of the software, and that is what's done. Now, the other interesting thing about this also is that these values are also what are called byte swapped. So each 2-byte pair is actually, at least according to a Linux machine, is backwards. That's called, and I forget. I always forget which one is which, but it's the difference between what's called little endian and big endian, and you can look that up. I'm not going to try to explain it. It's just a byte order, right? So yeah. So here's how this program Octal Dump has interpreted these unsigned short integers, and yeah, take these for what they're worth. What I'm going to do is I'm going to scroll down here, and you can sort of see, if you can see what these are, right? These are being sort of interpreted as like letters and the number 200, right? And I don't really have an explanation for why it's doing that. That's just what it wants to do. I'd be able to investigate this if I wanted to, but I don't really care. What's important to see here is that all the letters are sort of in the same part of the alphabet, right? We're seeing N's and T's and S's and Q's and R's and W's, right? So not a lot of anything else. So what this is telling me, right, is that this portion of the image is sort of flat, right? I mean, there's nothing really there, right? So yeah, we're looking at a piece of the sky where there aren't any stars, right? So it's pretty flat around here, and it changes a little bit, little changes. But what I'm looking for is what could be interpreted as a star. And that's when you start seeing these numbers changing in sort of a patterny way, and we'll get to that here in a second. I'm still looking for a star. Scrolling down through this file. Oh, there was something. Maybe I can go back, see if there's another one. I'm sure there'll be another one. Not seeing much change here. Oh, there's some. Okay. All right. Let's go back here. Now, of course, I know what I'm looking at and trying to explain it to you folks. That's going to be a little bit hard. But what you can see here, right, is that these numbers have changed. They've changed, right? So instead of having, sort of letters P, Q, R, S, T, U, right? We're seeing like lowercase f, lowercase e, lowercase b. There's a couple of other things, and then it goes into numbers here: 205, 203, 207, blah 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 blah, right? So then if we scroll down a little bit, we'll see there's another sort of group of numbers. And if we scroll down again, we'll see another group of numbers. Scroll down again, we'll see even a larger group of numbers. And strange characters, right? There's another one up here. There's more. There's more. And see, it's sort of getting smaller now. Sort of getting smaller. A few less. A few less. A few less. Oh, there's a little bit more there. Yeah, I mean, it gets complicated, especially we're sort of towards the middle of the file. Well, that's where I put these stars, is sort of right in the middle of the field of view. Now, I don't expect you guys to be able to follow this or understand this. So, do your best. It's not easy. All right, Jill, take care. See you later. You got to wake up early. Yeah. Take care. See you later. Thanks for coming in. But the interesting thing here, let's look at the number of bytes between these corresponding groups of numbers. Okay, so let's just take this one. So this number 241 here, actually this number 200, 241, right, is at byte number 230,000. All right, so let's go 230,000, entering that into the calculator. So now let's go back up to the previous group. So somewhere here, right? And that's at 228,448. 228,448. So that's let's let's see. I forgot where that other one was. Let's do this. Do you see how there's like maybe four rows here of interesting numbers, right? I mean, these are all T, R, O, P, and then it starts getting interesting, and then it goes back. But there's like four rows here of interesting ones. Let's take the third row. Let's take the fourth row again. Sorry. Let's go say 230,000. Byte number 230,000. Then I'm going to go back up to this one, and I'm going to take sort of the same last row. So there's only like maybe 3 rows here, but let's just take that one, right? So I'm going to subtract 228,464 from 230,000. 228,464, and I get 1,536 bytes, right? So that's how many bytes are between sort of this group of numbers and that group of numbers. Now, as you recall, every single pixel on this camera is 2 bytes in size. Every single number is represented by 2 bytes, right? So I got to take 1536 and divide it by 2. And lo and behold, what I get is 768. So that means that there are 768 pixels between what we're looking at here and previous group of stars. Well, that turns out to be 1 row in my image. So bottom line here is that what we are looking at is a star, right? It's the numerical representation of a star, and these numbers, sort of weird as they are, because they're being interpreted in sort of a weird way, and you can ignore that. But these numbers are the actual analog to digital values of these pixels based on the intensity of this star, right? So I mean, faint stars are going to have small numbers, and bright stars are going to have big numbers, right? And as we move more towards the center of the image, which is where I tried to keep this data in the center, we're actually seeing, here's one star, here's another one, right? Right next door, just a few pixels down, right? So, we're sort of seeing a pair of stars. I'm not going to claim that this is the binary pair that I saw. I would have to actually calculate how many bytes are between there to see how many pixels apart they are. But my guess is that might actually be the binary star. So yeah, Fitz saves the actual analog to digital numbers, right? So yeah, there is no compression, there's no kinds of interpretations at all. It's just a big list of numbers. That's all it is. Now I did do this in a different way, but I don't think I'm going to like what this is showing. So this is the same data. This is actually the header. It's just being interpreted as those unsigned short integers. So yeah, I mean, it's just a bunch of numbers, right? But here again, this is at byte 2880. This is where the actual data starts. Now, these are integers between 0 and 65535, but as I said, the bytes in here have been swapped. So these really aren't valid numbers, but let's go and see. You can sort of see that all these numbers are about the same, right? Yeah, more or less. 19,000 to 22,000, varying a little bit, right? But let's see if we can find, let's just scroll down again. I'm going to maybe grab scroll down and see if we can see. I don't know if we're going to be able to see any patterns in here or not. It's not as easy to see these because it's all numbers. Yeah, I'm not. And because the bytes are swapped, it's really we're not really able to see things as well as I thought, which is sort of what I expected. So, all right, well, I'm not going to mess with that anymore. I'm going to come back over here, and I'm going to stop sharing. And wow, it's already 3:11 UTC. That means it's that means it's 4:11 where Tim is. Tim, it's time to get up and start the day. Yeah, uh, if really, really, Tim, and everybody else, the for me, right, the only way to really, really grasp this stuff is to work with it, right? Just being told, formats and layouts and specifications and stuff. Uh, you know, I understand that that's not going to help much. Um, but actually working with the data, and these file formats, you learn pretty quick, and it's really not all that hard. I mean, I guess there's a lot of details, but even those, I mean, after a while, it's like, okay, yeah. Because that data, of course, um, can be represented in or stored um, in different ways also. Um, this data I showed you here is in unsigned short, but there's unsigned long, there's short, there's floating point, there's double floating point, there's double short, there's double long. Um, so any of those, um, I mean, it's just a list of numbers, right? And it's up to you, to tell software, what kinds of numbers are they, right? Are they um, um, integers? Are they floating point numbers? Are they characters, right? You have to tell software that, and you do that inside of the header, right? So you just have to have software that can read the header, and say, oh, okay, the data that follows is unsigned short, and that's it. That's it. And then it does the rest. It does the rest, just like magic. Magic. Yeah, it sounds um, um, boggling to the mind, but it's just like anything else, right? I mean, every single thing has its complexities, and once you get into it, it's no big deal, right? Right. So yeah, don't sweat it much. Just realize that, yeah, that fits really isn't like other file formats, um, like JPEG or um, 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 GIFs, PNGs, um, MP3, MP4. You know, those formats are pretty different. I mean, fundamentally, it all does um, come down to data, right? But in the case of fits data, those are actual um, uh, um, physical values, right? A certain amount of light has fallen onto a pixel, and um, uh, when that charge is moved out, um, a voltage is produced, right? And that voltage is then converted into a number, and that's what is stored inside of the fits uh, file, in the data portion. Now, when you're talking about GIF or JPEG, that's a different thing, right? I mean, yeah, it's still intensity, but it's also, I think, in terms of position, in terms of color, there's color map, there's all these other things, compression, all of that. Fits is just straight list of numbers, and that's what they are, and that's it, right? Um, so, all right, it's yeah, Tim, it really isn't too complicated. It's just a few little things, and look, I mean, I've worked with FITS files for uh, 30 30 years. So, it's sort of like that, right? It's like the back of my hand. It's um, and look, if you deal with anything for 30 years, uh, you're gonna know it pretty well, right? It's sort of the 10,000 hour rule, right? Um, um, 10,000 hours. It takes 10,000 hours to master anything, right? Well, 30 years is a lot more than 10,000 hours. So yeah, I've got I've got at least basic fits down. Now, as I said, um, right at the beginning, that there's extended fits as well, and extended fits, there is no limit, right? You can store anything, anything at all. um, GIF images, MP3 files, uh, you know, um, as I said, you know, next year's menus, uh, anything, right? Text, um, whatever, um, tables, just anything. But that's fits extensions, and that's sort of a different topic, and that's actually something that I've never really gotten into too heavy. Um, I understand it enough to be able to use them if I have to, and that's it. And that's it. So, all right. Well, I think that is enough talk about that because I'm having fits. So, cheers. All right. Well, I hope everybody has a great evening, a great day. Um, if you're new here and have just sort of stumbled in, um, um, stumbled into this live stream later on, this is just a casual, fun get together of friends that are sharing a common passion, the passion for the universe, and trying to understand it and trying just being completely amazed by it, and using this science of astronomy to maybe get a little bit of a handle on it, just maybe, maybe. Um, I still, you know, I still think that we're as far off as we we have been, for thousands of years. But yeah, you know, I'm closer to infinity, I guess, right? Right. So yeah, we're doing our best, and yeah, I think it's a pretty good process. I think it does allow us to maybe understand things really well, but it can also confuse us a lot too. So we just have to be, skeptical and open-minded. That's the whole thing, and curious, extremely curious, extremely skeptical, and extremely open-minded. If you can do those three things at the same time, you can call yourself a scientist. And yeah, look around and and go, wow, I'm going to try to figure that out. So, all right. I'm going to get out of here for now. Take care. Yep. Thumbs up if you wish. Thumbs down if you wish. Make some comments. Thanks, Tim, for coming in. Thanks for the comments. Those are really, really nice to see. And thanks for getting up or staying up. You're just a crazy man. So yeah, but crazy is my kind of people. So cheers. All right. Take care, everybody. I will see you on the spin. Little less than 23 hours. All right. Take care. Bye.